Okay, we are going to start. Welcome everybody to this webinar. So this webinar is organized in the framework of the ESCAPE Summer School for Data Science, and also in partnership between LAP, so the Laboratory of Particle Physics of ANSI, and LISTIC, Laboratory of Computer Science in ANSI as well. And today we welcome Professor Ofer Lahav, who will present us and talk about artificial intelligence in cosmological experiments. Okay, the floor is yours. Professor, you have 1 hour.
Thank you very much, Alexander and Thomas, for inviting me to give a talk at this school. Looking at the program seems very broad and interesting, and I understand there are people on the line who have quite a lot of experience in this field of machine learning for different applications in physical sciences. So what I try to do is sort of a bit of a big picture, with examples which are admittedly are from our little corner work I've been doing in recent years with students and postdocs. But I think you can think of them as examples which can be generalized for other problems of interest. I'm normally based at University College London, but at present I'm actually on a short sabbatical in Oxford, so I'm actually talking to you from Oxford. And in case you wonder what is this picture, we'll come to it later, but this is a picture of a reconstruction of dark matter. That's in that region you see here, and for orientation also a picture of the Milky Way and the Large and Small Magellanic Cloud. We'll come to it. And these are just acknowledgements to various support from UCL and this Center for Data Intensive Science, which I'll talk about, and STFC. Previously, I held an ERC grant, and this is the college in Oxford, All Souls College, where I'm a visitor this term. So I'll move now to the next slide. Yeah, so the outline is, it's going to be a mixture of giving you the summary of, it would be a summary of telling you what is the status of cosmology now, and also especially new results that just appeared about 2 weeks ago from our dark energy survey. And then I'll move to the AI part of the talk. I thought I'll do it as a mixture of the two, and I'll do my best, obviously, to leave time for questions. So I just wanted to say from the beginning, credits and many thanks to collaborators and postdocs and PhD students over many years. This is a subset of them. You'll see some work by some of them. A picture, at a meeting over 2 years ago when we could still socialize properly. And I hope that soon we'll be again at that situation. And I mentioned it briefly, but maybe it's relevant for this forum that we started about 5 years ago. We started a new center at UCL, and that's it's called CDT, Center for Doctoral Training in Data Intensive Science. There's a website there. And what's unique about this program is the PhD students in total spend 4 years in this program, but along the way, they do projects with group projects with industry. You can see about 20 different industrial partners. Some of them you may know, like the Economist magazine, ASOS, the BBC, and so on, the London Underground. And they also spend 6 months of the 4 years. They actually spend with one of those companies, and they do machine learning and AI there. We have now students from 4 years, and in October we'll have the 5th cohort. Of course, the first cohort will be finishing in September. At the moment, we have 45 students, and again, they do a mixture of the PhD project itself is in particle physics or astronomy, but then they have all these industry connections, so they develop what we call a dual career. And I've been very fortunate that 4 of those 45 are students working with me, and you'll see later some of their results is Konstantina, Ben, Sunil, and Prab. Okay, and also just to say, it's at the bottom there that we have a spin-off activity with Jordan, where we have a group of students there of about 40 or so students, and that's going well online. Unfortunately, we cannot do it in person as I planned for now, but we also give them a course in machine learning and so on. Okay, so I just want to, you probably hear talks from different people in this summer school and also at your universities, and you probably have different versions of AI. I guess there's a whole spectrum. I guess there are people who love AI and would tell you that this would solve everything, that everything will be controlled by AI. And even AI will do, robots will do research, and robots will write papers, and maybe robots will write PhDs. And it goes all the way to the other spectrum of very suspicious. People are very suspicious of AI and maybe a bit afraid of it. Could driverless cars actually work? Could you trust the algorithms? Would you trust your doctor, medical doctor, if they tell you that that you need to undergo an operation because machine learning algorithm said that without explaining why? So there's a whole range of this, and I think we're right to ask many questions about this, also ethical questions. And my own take on this, I kind of belong to that school of people who talk about augmented intelligence. So I'd like to think of it that we have laws of physics, we have human knowledge, and we have all this AI machinery, which in recent years has really developed. And I think those things should talk to each other. In other words, we cannot neglect the knowledge accumulated in physics and just say, oh, we don't care about Newton's laws, we don't care about general relativity, because AI will just find it. I think we have to somehow connect it, and also to come back with results from AI to the humans and say, does it make sense if I discovered an anomaly in the data, for example? Does it make sense? So I'm just telling you my philosophy from the beginning, and you'll see it through some examples. And this is just a little bit of explanation what what is meant by augmented intelligence. It's not, I've not invented it. It's in the literature, but it's basically cognitive technology that is designed to enhance human intelligence rather than replacing it. And it reinforces the role human intelligence plays when using machine learning and deep learning algorithms to discover relationships and solve problems. Okay, maybe in question time, if people have different opinions, I'll be interested to hear that. Now, let me spend a little bit of time about cosmology. I know some of you are cosmologists, others do other parts of astronomy, and then there are also particle physicists and maybe people from other fields. So I'll try to give you kind of a very broad picture of what's going on. I think it's now, some would say for 20 years, I would say for 30 years, depends whom you talk to. I think there seems to be a consensus and agreement about what's the universe made of, with about, at present day universe, it's believed about 5% baryons and let's call it in round number 25% cold dark matter and 70% dark energy, which is some kind of a generalization of Einstein's cosmological constant. And one question is this, do we agree with this? So when you do a new experiment, you send a proposal, we would like to verify if this is true. And also the question is, what is the dark energy? Is it just Einstein's cosmological constant, which he hypothesized in this paper written in German in 1917. So this is a very, quite important that Einstein just put it, as you know, he put it as a constant in order to get a static universe. And now the value we find does not produce a static universe, obviously. It shows that the universe is accelerating. So in this diagram, you can see the evolution of the universe and then this acceleration, which started about 6 billion years ago. Okay, and that's the picture you see in almost every conference in cosmology. And the question is it right? So how do we find it? Of course, we don't just look at the sky and we see lambda equals whatever. We have to do it because you come from algorithmic background. It's an inverse problem, basically. We measure something which is very complex, and this something is some sort of integral over other things which represent astrophysics and some selection effect. So maybe the most famous probe are supernovae. These are these exploding stars, which are made of two stars actually, and one Pro's method, the other one, and then there's an explosion, and they're called supernova type 1a, and they seem to be standard candles. In other words, you can use them. Think instead of the candles, you're thinking about the supernovae, which is this picture here. There's an explosion, and it turns out that the light curve, after some manipulations, you can standardize it, and there's the standard candles. Equally, you can use standard rulers. So apparently, when you do Fourier transform of a galaxy map, there's some nice peaks there, which you have fully understood in terms of physics, and they can be used as standard rulers. And you can have similar standard rulers also at the cosmic microwave background. There is this effect called gravitational lensing, also worked out by Einstein, that light gets bended as it passes near massive objects, or in Einstein's language, as light passes through curvature of space-time. So distant objects, when they reach us, they look distorted. Here you see a highly distorted image. So the galaxy itself is probably very simple, but we see this huge distortion. This is called strong lensing because what causes the lensing is a big cluster of galaxies. But in fact, every distant galaxy, like here, will get distorted at some level because there's lots of stuff going on from there to us. So maybe if the galaxy itself is a circle, what we see is some sort of maybe banana shape or elongated shape. And this way we can learn about the expansion history of the universe and the dark energy. We can also learn, as I'll show you, about the mass clumps in between. So it's a beautiful method, and I'll show you, in this diagram, I show you two galaxies which were distorted. I'll show you results in a few minutes. I'll show you results which come from 100 million galaxies, 100 million galaxies with shape measurement. So it's interesting how this field is progressing. We're lucky to have big questions, big surveys, and big data. And this thing started, so Big Bang, all the way to the present. I just went through this before with the other diagram, but there's the period of the cosmic micro background, where we see the fluctuations there, and then when the universe became reionized and our structure. And luckily, we have all these wonderful experiments which are either working or about to work that can give us lots of data. So I think for the young generation, the next decade or two is going to be a wonderful period in terms of data. And you may ask, why do you need so many experiments? The answer is, it's good to check, right? It's good to look at the same problem from different angles, and each experiment is a bit different, and they complement each other. Okay, so this is a bit of a close-up on some of the surveys, and it's a bit biased because I happen to be a member of those 4 collaborations. In particular, I spent 17 years on this survey, which is called Dark Energy Survey, DES. I'm also involved in DES-Z, which is Dark Energy Spectroscopic Instrument. And then these two are being planned or being constructed. One is on the ground, in fact, on a hill in Chile. This is in Chile, this is in Arizona. So this telescope called LSST, and more recently, the observatory is renamed after Vera Rubin, is being constructed. And of course, there's the European flagship project, very impressive, called Euclid satellite. Okay, now some of you are more familiar with data in particle physics, which is also in astronomy. We have also lots of data, and that's why, of course, our fields lead the way in terms of data science compared with other fields, although other fields also have now lots of data. So this is just to give you an example. I showed you DES and DESI. So DES generates about 1 terabyte per night. DESI is spectroscopic, so it's a bit less. Rubin will do, I don't know, 15 times more than DES per night. And Euclid space mission, so it's a bit less. But the square kilometer array, which is a radio survey, this will be generate huge amounts of petabytes. And the number of objects, of course, we also look at stars, but for us who do cosmology, look in galaxies, you can see when I did my PhD, I used a sample of about, I think it was 20,000 galaxies. And then I was in the 2DF survey with, we generated 250,000 galaxy spectra. And you can see with this imaging survey, there's hundreds of millions. And eventually those surveys will give billions of objects. So I don't need to explain to you why it's relevant for data science. Of course, the cost goes up. And by the way, one should really be careful to factor in computing costs into this. Not that to say there will be data, but you have to think about hardware and also time for research software engineers. I think we're entering a new era that we have to factor in the same way we in the past factored in the time of technicians and engineers. Now we have to think about the time of data scientists, right? And that's the number of scientists also goes up, from tens to hundreds to thousands. So this is the picture. Now, I was already said I've been involved in dark energy survey for many years. It's a multi-technique approach, and as I said, produce 100 millions of galaxies and thousands of supernova, 400 scientists from 7 countries. Observations actually finished in 2019, but it takes a long time to analyze data. And we're lucky, so I'll show you results that appeared on the 27th of May. So I think it's the first talk I'm giving, because I gave several talks before we could announce the results. So I'm pleased finally I can say, instead of just saying there will be results, I can say here are the results, but this is only from 3 seasons, so it's 50% of the data, and eventually there will be the full release. The telescope is in Chile, as I said, and that's the optical corrector, which is, it's a camera, just like the camera on your smartphone, except that it weighs several tons and it costs $40 million. So this was in 2012 when we inaugural ceremony of that. So it's a long story. I'm telling it to the young people who are joining now, long-term projects. It's a very long journey. So we've been engaged with this myself 17 years. And I think we come to the point that really these projects go over many decades. So we actually edited this book, which tells the story of dark energy survey, how it was built, the cosmology science, non-cosmology science, and even reflections with some chapters on philosophy and anthropology and art. So maybe if you're interested in kind of getting into this big collaboration game, maybe you can find it interesting. Okay, now finally I promise. So on the 27th of May, the collaboration released results. It's based mainly, the impressive thing is this 100 million galaxies with shape measurements, which are used for weak lensing, and also many millions of galaxies for clustering. And you can look at the website of the Dark Energy Survey, and there are all the there are about 30 papers there, and you can also look at the archive, electronic archive. So you can see many technical papers. Of course, there are 400 collaborations in 7 countries, so different subsets of people are involved in different things in a collaborative way, of course. And I was fortunate with a PhD student of mine. He's now a postdoc in Paris. His name is Niall Jeffrey. This led to this map of dark matter, okay? So regions which are bright are overdense, and regions which are dark are underdense. And this is the larger area. It's about 5,000 square degrees, and I already mentioned that the background is just the Milky Way for orientation. So this was done by some sort of a version, if you love, of an AI algorithm. I'll show some technical slides. And we got some publicity 2 weeks ago. So this is from the BBC Online, and it also went to BBC TV and some journals and so on. There's also a nice summary in Nature magazine. But as I said, there are 30 papers, and the collaboration, and I should say that quite a lot of the work is led by early career scientists, people who are PhD students and postdocs that have done an amazing job. And this was the core analysis. It's called 3 × 2 point statistic. It's a bit of a jargon, but what it means, you take the clustering of the galaxies, in this case 11 million, and take the weak lensing, and you can easily see if you have 2 methods, you can do the autocorrelation of one method, A method A, so AA, and you can do the cross correlation, the autocorrelation of method B, so it's BB, and you can do the cross correlation AB. So that's where you get this triangle, and that's called 3 × 2 point. So this is a huge amount of work, and I can refer you to this. This is like the key paper that summarizes everything. It's in alphabetical order, and it also gives you in the appendix links to the other subsets of papers, and you can look at that. So the bottom line in this analysis, it assumes about universe is made of, you need 6 parameters or 7 if you want the equation of state of dark energy. So that's what this W is, it's pressure over density. So if you want that to float, you have 7 parameters, but there are about 25 or so nuisance parameters. Parameters you're not directly interested in, but you have to put in. And what you can see, for example, in this equation of state, against the matter density parameter, you can see the dark energy survey is in this orange, in green, and the orange is the, the green is the, sorry, I confused you. So slowly, the green is the cosmic micro background, Planck, and the black is the dark energy survey. And if you combine them, you get the orange, okay? So you can see they're not exactly on top of each other. Of course, it's a projection 2D of our dimension, but there is correspondence, which allows you to combine them, okay? And the bottom line, if you combine it also with other things, is that W comes to be very, very close to -1, which is Einstein's cosmological constant, okay? You can look up textbooks, and when W is exactly -1, the density of that component does not change with time, and it's Einstein's cosmological constant, and the error bar we get here is now 3%. So it depends how you look at it. You can see even in the newspapers, 2 versions, you can say, it's wonderful, it's a triumph for this cosmological constant and the Lambda Cold Dark Matter paradigm, which is true, I agree with that. At the same time, there's some slight deviations. And I say slight, these are things at the level of 2 sigma or so between Planck and the DES, but of course you should not close your eyes and actually try to understand why. So this is dark energy survey. I can refer you to those 30 papers. There's another project, the names are confusing. The one I refer to is called DES, it's called DESI. Dark energy survey is photometric, this one is spectroscopic. And the good news there is that observation started. Again, some of the optics for DES and DESI was constructed in our basement at UCL, but also in many other institutions. The lead institution of DESI is Fermilab, and for DESI it's Lawrence Berkeley. And observation started, and due to technique of multi-fiber, we'll see 35 million galaxies with spectra eventually. But I don't want to hide, Lambda CDM is doing well, but there's this tension, some disagreement about the Hubble constant, which is the rate of expansion of the universe. And one group says it's 73, the other one says 67. And there are many techniques, you can see it here, it's double constant, different values. And it looks like really somehow the early universe probe, like the cosmic microwave background, gives a low value, while the nearby Cepheids and supernova and so on give 73. And I'm actually nearly there with a review article with Paul Shai and Pablo Lemos that summarizes it. And the big question is, when things disagree, is it systematics or new physics? We gave them some grading for each experiment. I think I'll skip it. It's a traffic light method, and when the paper is out on the archive, you can look it up. There is another technique called gravitational waves, sirens, and you can basically combine the information from a gravitational wave about the distance to an object with the redshift of that object, which you can find if it has a counterpart. At the moment, there's only one object that has both nicely, both the gravitational waves and the optical, and so we call it a bright siren, and we hope there will be many others, and that's an example of this H0. You can see it's quite broad, So at the moment, it's consistent with both Planck and the local distances, because the error bars are big. You know, when you do an experiment, your error bars are big. You keep good friendship with everyone because it agrees with everyone. When you narrow it, of course, you have to defend it. And again, I was very fortunate to have those students working with me, Antonella Palmassi now in Fermilab, and Konstantina Nicolau, who is still at UCL. Okay, now I finally move to the AI, okay? I mean, I just thought it's good that you understand the background. So probably from other talks, again, depending how the other presenters talked about it, at what level of enthusiasm and criticism they've talked about AI. But I think we want to connect it. So in cosmology, there's quite a lot, you know, this approach of Bayesian approach is very widespread. And I think it would be good if when we do AI, we connect it to that. It's very important to, are we able to interpret and explain AI? So it's not just a black box. I think there's a big issue on how to minimize biases when we have incomplete training sets. So if you train your algorithm and told it that 80% of animals in the world are dogs and only 20% are cats, but maybe if in reality it's 50%, 50%, then when you show real data, you will show a biased result, okay? I think you get that point. I'm personally, and many others, of course, interested in the question, should you include prior physics? Should you tell the algorithm about Newton and Einstein? Or should you let it figure it out on itself? And how can you leave room to discover new physics, to discover something new? Okay? Now, usually, I think what I tried to say when I showed you lots of data, the usual argument people say, why using AI? You say, oh, because I have lots of data. I cannot ask a student to look at 1 billion images to tell me if they see something special. But I would like also to make the point with this illustration here that also the human brain, we admire the human brain, but it has limitations. So this is actually not an animation. It's a static picture, believe it or not, absolutely static. But you know, if any of you can see all 12 points same time, send a message in the chat, okay? I have not met anyone yet who could see those 12 points same time. So I'm not a neuroscientist, but apparently the brain has some limitations for that configuration to actually see all these black points at the same time. The brain kind of jumps from one to another. So to me, it's quite interesting because, you know, maybe you have to check when a medical doctor tells you that they identified a tumor, and also when someone told you they found a new galaxy. You know, maybe it's an illusion, but that's why I've said we can augment one with the other. We can combine the information and show it to the experts. Now, I think I've seen that you have, from looking at the material on the website, I could see this. You talked quite a lot about things like scikit-learn and TensorFlow. So I think you know all that, so I can skip it, but these are broadly the areas we cover, which are mapped nicely into astronomy. So there's classification and clustering and regression and so on. So coming to, I'm combining now things I told you about the cosmology and what we actually do. So, you know, in machine learning, this goes back to the 1980s. It was clear you can do supervised and unsupervised. There are algorithms which maybe we don't glorify as machine learning, but for example, PCA, principal component analysis, it's a nice way to do some unsupervised analysis and also to compress data, another story. But of course, there's supervised where you teach according to examples. You say, these are dogs and these are cats and so on. And then there's a huge range of algorithms, and I'm sure probably everyone on this call already practiced neural networks and decision trees. People think decision trees are easier to understand because you ask about physical parameters and you can tell based on that, if you look at the sample of galaxies, based on certain parameters, bulk disk ratio and so on, you can tell what defines a class. And neural network, which I like, I used it a long time ago, last century, in the early 1990s, we used already neural networks then, is a bit more difficult to understand what it does, but it does pretty well. And as you know, the reason the subject has expanded so much to the level that you have this summer school and we have this program and so on, and the whole world is now brainwashed with AI. I think one reason is the development of deep learning, which we'll come to. And I think one question there is why is deep learning so successful, actually, right? It's not fully understood. And in terms of applications, some of them I think are quite straightforward. For example, classification from the point of view of idea is now simple. You know, it was very novel at the time, but now I think it's quite simple to think about an algorithm that would tell you what's a star, what's a galaxy type, what's a supernova, and so on, type of gravitational waves. One can use regression to basically get a parameter. This is shown in photometric redshift. So all these techniques in DES use just photometric redshifts, right? So we don't quite get the redshift of the galaxy. We just get the galaxy in several different colors, say 5 colors. And then you can use artificial neural network to predict the redshift based on a training set where you know the true answer. So I would call it kind of regression. You can also derive the cosmological parameters. And of course, there's this whole area of generative models which enhance simulations. So I mentioned a bit that I had quite a lot of fun in the early 90s. I think we published a paper, an early one in 1992, and where we used some galaxy properties, about a dozen or so, and we also showed a small sample, 840 galaxies, to galaxy experts, and we asked them to classify it, and then we trained machine learning on it, okay? And it worked pretty well, and this was a paper we got to Science, where I basically had a list of very famous astronomers, like the Vauquelin was one of them, we show that it can work. But I can tell you, when you do something so early on, people, for most people, it was like on the fringes. They say, why are you doing it? Why are you doing it? And I said, look, there will be one day billions of galaxies. But it was kind of a bit ahead of its time. But I'm very pleased I spent time on it. It's also an encouragement to young people sometimes do something which is off the mainstream, off the beaten track. I discovered that Nikos Konstantinis, who is the other co-director of that Center for Data Science, he himself also did some work at about the same time in his PhD on neural networks in particle physics. So, some people think AI started 5 years ago. No, it started in the 1980s in its capacity, depends how you define it. And there's some work, but not as intense as now. Okay, so one thing we did, I mentioned, we showed image. We got people to look at images, and then there was some processing to go from those images to parameters, and there was classification by human, and then a neural net reproduced it, and then we used the Galaxy Zoo, which is a major survey, where a major facility where members of the public classify galaxies. It's led by Chris Lintott, who is a professor in Oxford, and I'm pleased to say a former student of mine. And it seems pretty, no, the classification is well over 90 but there's quite a lot of attention, not by us, by other groups, to also pay attention to outliers, to see if you find anomalies. This is another old paper we did with computer scientists, where we use galaxy spectra and using information theory concept. So this is some normalized information. We could show how much information is there in spectra, how much information. And it shows really that you can classify objects to about 5 classes, which is probably what most astronomers would do. We also classified with a former postdoc called Michel Lochner. We classified supernovae to tell if they're 1A, and you can see their data. It was done on simulations and it's trained, and different techniques to compress the data, and then different algorithms, naive Bayes, nearest neighbors, support vector machine, artificial neural networks, and boosted decision trees. And you probably know this type of diagram. It's called the under the curve diagram, and you would like it to go all the way to 1 and stay there. You can see that something like naive Bayes fails, and the best one in this game was boosted decision trees, which gave nearly 95%, 97% of the area under the curve. Okay, I mentioned photometric redshift. So again, I remember I was young researchers and someone told me, oh, we don't know how to go, there's 5 numbers of 4 in this case, we just want redshift. And I thought, oh, let's use neural nets, because we knew how to do this for the galaxies classification. And I thought it's a very easy, inverse problem, but look, even now people still work on it, and many people produce clever algorithms, and that's essential for Euclid and LSST. We produce these 2 modest packages. One is called ANNZ and one is called NZ2. And photometric redshift is quite annoying because you wish you could have just a spectrum, which we're going to have with DESI. But in terms of an exercise for machine learning, it's a very beautiful example because it's, students love it. So I usually get students to do a project on that because conceptually it's nice and it's useful. Here, I don't have too much time to go in detail, but this is a current CDT student called Ben Henges. What we've done with collaborators at RAL, Jayan and others is to do what's called benchmarking, to see how well you get the machine learning to work in terms of the training and testing time and also performance. So this shows the time it takes against number of training objects. And these are 1, 2, 3, 4, 5, 6, 7 algorithms, right? And it's interesting, obviously it takes longer, but some of them level off. So it's non-trivial scaling. And this is done in a million objects, but when we move to the billion, this would be very important, right? With another student, Sunil, and a former postdoc with Hartley, we use this photometric redshift not only to tell the redshift, but also to tell the stellar mass, the amount of mass that comes from stars. And it's a 2-dimensional diagram, and it's the same object. The truth is in gold and the estimation in white. And the reason this looks much better than this one is because the training set was much, much better, okay? I don't have time to go into details, but that's what it is. Now we move to deep learning. And here, you probably heard about it, right? I think it's fair to say that deep learning is a subset of machine learning, which is a subset of AI. And you can see the number of papers on the electronic archive goes up and up and up and up and up. And it's about something like 90 per year now. And the key idea is that if in the past, when we classified galaxies, we would take, say, a picture of that object, of that object and do some pre-processing, tell but it's got two circles and so on. The new thing, deep learning, you show the whole image. And I've seen on your program that you have sessions on deep learning. You'll probably practice it if you haven't done it. So it's quite amazing, but maybe some computer scientists can correct me. I think there's no easy explanation why it does so well. And this is just an example. As you know, you take a picture, you convolve it with filters, and you then do the classification and decide if it's a bird or sunsets or a dog or a cat. So if you like, what used to be pre-processing is now done through those filters. This is an example of simulations of lensing. I showed you lensing before, and this is a group, it's not us, but they've done a very nice piece of work and show that. So here we have simulations with arcs, which are produced by this lensing effect. And here are no arcs, and of course you can ask many people to look at it, which is fine, but it's time consuming. So here it's a CNN, a convolutional neural network that managed to do successfully do it in about 90%. We also have problems, what we call deep blending. So as we go very deep, for example, with Euclid, LSST, and so on, as you go very deep, you start seeing overlapping objects, and you want to decouple them. So you have the CNN to break that into two. Okay, that's very important because these are the objects that go into your analysis. Now, I showed you the very first slide, this dark matter, and also the publicity we got 2 weeks ago. This is from the previous patch of the sky from DES. And again, using a technique which you can think of a little bit as some version of AI, one can get a map, like a heat map. And when it's red, it means it's over density, and when it's blue, it's under density. And in fact, but this is dark matter. It's actually dark matter. So to recap, how do you actually see dark matter? You don't see it, of course. But what you can do is use distant galaxies and use their distorted images to learn about what's between them and us. Okay, I showed it in an earlier slide. And then after you do it, you can do some sanity check and look, is this region also rich with galaxies? Is this region very empty of galaxies? And the answer is yes. There is correspondence between the dark matter and the galaxies. So here, Niall Jeffrey, my former student, produced different maps, different techniques. This is Wiener filtering, which probably most of you know. This is a method developed by a group in Saclay called Glimpse, and this is a Kaiser-Square algorithm, another one. And this is just an example. And then what's shown here is another approach of using deep learning. And what you do here, you train the computer, the algorithm, with many simulations. In this case, 3.6, 10 to the 5th simulations. And then you show the one universe. And what you do is this simple equation represents the link you have between what you measured, which are these distorted images, which I showed you earlier, and what's called kappa, which is the projected mass distribution along the line of sight, okay? And that's the noise. So really, for those of you who come from different fields, other than astronomy, it's no more than an inverse problem, that you have observables and you're trying to find something else. And this is a bit of formalism and a bit to demystify that you can see all this is some kind of minimization of a quadratic form where this F of gamma giving kappa is the mapping between the distorted images and the projected mass. So you can really think of it very much so as an inverse problem. And this is not us, that's a group in Paris that has gone another step further. And what they do, they show the algorithm lots and lots of simulations, and they predict the actual cosmological parameters, okay? So if you like to think about summary statistics, instead of doing 2-point function, on the maps. They actually showed the whole map, one after another. They showed it to the algorithm, and they asked to derive some parameters here. And this is a map of the clumpiness factor, sigma 8 against omega m, and you can see the Planck again is the winner. You get very good agreement, but and if you do 2 point, you get things which look a bit broad, but it's really the using CNN brings you to this purple one. Yeah, so there's some hope there. Now, Thomas, maybe I think time is getting short, so I think I'll skip this part of the talk. I'll skip it. If there's time during questions, I can refer to it. That's a completely different exercise to get the mass of the Milky Way and Andromeda using AI. But if there are questions, I'll address that. Otherwise, maybe I should stop here just with the conclusions that cosmology is undergoing industrial revolution in both spatial and temporal domain. But there are challenges. I think we should not, the subject is mature enough, we should not oversell AI now. And we have to be aware of incomplete training sets, how to incorporate physics, understanding the algorithms, and benchmarking, how to scale it up as the data go. But whatever we do, I think it's a great training for PhDs, postdocs, and staff to do things beyond academia. So, our students in that program do all sorts of other things. I'm sure physicists who switch to do a bit of COVID research using AI. So that's why I find this subject so exciting, that you can actually use it for other purposes. And would it produce new knowledge, or have we learned something new from AI? It's an interesting question. You should ask it in your field as well. But sometimes it depends. If you look at something which many people looked at for many years, you're less likely to discover something new compared with looking at something fresh. Okay, so Thomas, I think I'll stop here and I'll welcome questions. So thank you.
Thank you, Ofer. Thank you very much. For now, I don't see any question in the audience. I have questions myself, but maybe I can ask them after. So if you want to take 5 more minutes to go through the Andromeda example.
Are you sure? Okay, or do you prefer to ask your question? What would suit you?
Please go ahead with.
Okay.
Yeah.
Okay. So this is an example. I'll go straight to the AI. So you probably know that. I'm sure you know that we live in a galaxy called the Milky Way, and that it's falling towards Andromeda. You can see it there, right? So it falls at about 120 kilometers per second. And one day we'll collide. So there is a classical modeling which assumes only those two galaxies. And if you know the age of the universe, you can also get the masses of those objects. So there's an old history of doing it in simple ways. But then we thought, let's try it in machine learning approach. And we have 2 papers about it, actually. One by my former student, McLeod, another one led by my former postdoc, Lemos. And so this is the simple way: acceleration equals Newton's law plus the linear expansion, the linear force with lambda. And as I said, we're falling. I think this is the more precise number than what I said, 109 kilometers per second, and distance 770 kilometers per second, kiloparsecs. And it seems to do well, but then you can do this likelihood-free approach, likelihood-free inference approach. And what we've done is using 2 million mock pairs of galaxies. So from the simulations, 2 million that have pairs in them. And then we tested it on 10,000 pairs. And you can think of it as a Bayesian way. But the point is, you can finally show it our own Milky Way and Andromeda. And based on the knowledge for those 2 million pairs and those algorithms we described in the paper, you can then actually get the mass of the sun. It seems to constrain the mass of the sun to be about 4.6. 10 to 12 solar masses, still large error bar, but it's a kind of interesting of connecting simulations to data through machine learning. So that's it, Thomas. That's that part.
Okay, thanks. Very interesting. So I have a question myself. We see that we have much more data now in our experiments, and you showed also that we have an increase in the number of members in these experiments. Do you have more computer scientists now in these experiments, or should we train physicists to handle this data?
It's a very interesting question. In fact, we see when we advertise for postdocs and faculty, we see people apply from different streams. So you can have a computer scientist who loves astronomy or particle physics and then applies and learns the art. You can see the reverse, someone who was brought up in a more traditional physics astronomy, but becomes very interested in that, and using the tools we have in mathematics and physics can do lots with it. Personally, I think it's very healthy if we have a mixture. If we have a mixture of these people, because I feel I've been following this field for many years, over 30 years, and I find that sometimes in astronomy, we don't know the whole literature, right? We don't read the latest papers. So we tend to find something and we work on that. But if I had next door a computer scientist who could tell me, look, there's just this new paper with this technique, this would be wonderful. And likewise, I think for the computer scientists to talk to astronomers, practices would be very good. So I think there's a lot of room for cross-fertilization. But also, I wonder, maybe you have opinions about that. There's also now quite a lot of discussion that we need. In fact, I listened to a discussion about this morning by some discussion about roadmap of computing in Europe, computing for astronomy. People say we also need people who are not researchers writing papers, but they are more like research software engineers. So they can facilitate all this big activity without having to worry about the usual pressure we have in academia, teaching, administration, getting grants. That could be people, just the same way you have people who build telescopes, right? That's their job, to build telescopes, to have people who would do this, help us to do, if you like, all the background work in terms of big data. Yeah.
Yeah, thanks. I think I agree that we need really exchanges between astronomers and computer scientists.
But I should also add, in this program we have at UCL with CDT, one of the features is that the students have to be co-supervised by people from different fields. So the student would have one supervises astronomer, the other one computer scientist. So the students are then like the glue, and they get the others to talk to each other, hopefully. Yeah.
Nice. It's a good way, yeah, to make people talk.
That's right.
So there is a question from Christopher in the school, who's asking, I've not come across the idea of letting the artificial intelligence build its own law of physics before, or will the AI build its own law of physics, and would we expect them to resemble the law we build ourselves?
Okay. Could you just repeat it, because it was sure. quite long?
Yeah. If we let the artificial intelligence build its own law of physics, would we expect it to be like the true law of physics that we build?
Well, I think you can think about different strategies here. You can think about different strategies. You could, for example, enforce that some conservation laws. Right? You can say, let's say that the machine learning is trying to get energies of particles in some collision, something like that. So there's particle A and particle B, and you have the two energies. You could enforce the energy conservation, right? You could say, I would like the sum of the energies, EA plus EB, to be that sum, and it's enforced, okay? Which to me makes sense because I trust conservation, energy conservation. I trust it, okay? I feel it's a waste not to use human knowledge of physics. But you can think about another example that maybe we don't know the physics. Maybe, let's say, the particle physicists here, let's say we don't know if there is sterile neutrino or not. Okay, so there's some ambiguities, or maybe some deviations from Newton's law. Then maybe it's maybe possible to find ways to get the algorithms to discover something new, to allow a new delta, some extra knowledge, and then to come back to the experts and say, look, something in this experiment does make sense. There's some deficit of something, to look at it. So there's quite literature. I myself, I hope to spend time with students and others to look into that. I think it's very interesting. I think it's sometimes called physics-inspired machine learning or something like that. That is a kind of some sort of activity around that. So you may would want to look at that. But I think it's very important to say what is you're trying to find, so it's not circular, and you don't discover what you already assumed. Yeah. Thank you.
Yes, thanks. Another question from Didier, who is asking if the use of artificial intelligence in astrophysics and cosmology is only an academic effort, or is there some private companies like Google willing to involve some effort in that?
No, I think there is some crosstalk, and the question is whether Google would invest in astronomy, right? In that direction. So it's going at some, there is some activity at low level. I had, two postdocs actually did some collaboration with some individual in DeepMind, for example. And that's at the kind of more low level, just individuals. But you could imagine if you get some of these companies excited by playing with data, that they can use it as an example for illustrating their algorithms. So we talk to them, to these companies, and they're interested, and they like the idea of building some toy models using it. But maybe if you're thinking about a whole donation of billions of dollars, that's a different story. But maybe it will happen one day. There are some wealthy people who build satellites and so on. Maybe they will think, oh, let's build a satellite for astronomy. Yeah.
Yeah, we have seen also that Google is interested in other topics in science, like protein folding or things like that in academia. So
I think there's hope there. And remember, it's the people, some of the scientists to get a PhD go and work in Google. So they inspire the Google people to do it, right? And then, so it's a good two-way process, yeah.
Right. Okay, maybe last question. Will the AI figure out that the energy is conserved when exposed to different experiments?
Well, it could be. So you can build your network. You can build your network such that you don't tell it that energy is conserved, and you let all the different energy E of energy of A, particle A, and energy of particle B, and you look at their sum, and you see whether it's conserved, right? So I think it's quite an interesting thing to play with, and you know, you can even have some energy of particle X, which is the unknown, and maybe this way you discover a new particle. I know I'm not a particle physicist, but I can imagine you can. I personally, I think it's good to do it both ways. The nice thing about all this area of AI machine learning is this flexibility. You can change the architecture and so on. So I think it could be quite interesting to do it both ways and to see whether you discover it. You can be more ambitious and say, I like to do it to be a bit provocative. Imagine you take all the data collected by Atlas, okay, without telling anything to the algorithm. Would the algorithm discover the Higgs boson? Just by data without no physics? Or would you give them all the data from these big surveys? Would it discover Einstein's GR without anything? I doubt it myself, but maybe I'm a bit conservative. I think it does need some framework of physics, but you know, one can play with these things. These are interesting questions.
Yeah, very interesting. Okay, I think we have reached 1 hour, so we will end now. Thank you very much again for this interesting seminar. Thank you everybody who joined, and we will now continue with the Escape School.
Thank you very much. Thanks everyone, and have a good weekend. Bye-bye.
Bye.